For 30 years, scientists had a question they could not answer. A planet at the edge of our solar system was slowly bleeding heat into space, year after year, decade after decade, and nobody could explain why. The instruments weren't sensitive enough, the telescopes weren't powerful enough, the planet was too far away, and its atmospheric glow too faint to study in any real detail. So the question sat there, unanswered, for 3 decades, until now. The James Webb Space Telescope has just stared at Uranus for 15 hours straight, and what it found inside that frozen, tilted, deeply strange planet has not only solved the mystery, it has revealed that everything we thought we understood about Uranus was incomplete. This is the story of a 30-year question, and the telescope that finally answered it. To understand what Webb just discovered, you have to go back to 1986. That year, NASA's Voyager 2 spacecraft flew past Uranus, the only time any spacecraft has ever gotten a close look at this planet. What it found was extraordinary in the worst possible way. Uranus was cold. Not just cold, brutally, record-breakingly cold. Its upper atmosphere measured at minus 224 degrees Celsius, making it the coldest planetary atmosphere in the entire solar system. Colder than Neptune, colder than anything else we had ever measured. But Voyager 2 gave us only a single snapshot, a few days of data, and then it was gone. For the years that followed, scientists watched Uranus from the ground, blurry glimpses, incomplete data, partial pictures. And then, in the early 1990s, something strange started happening. The upper atmosphere wasn't just cold, it was getting colder. Year after year, measurements showed the temperature dropping further, a slow, steady, continuous cooling trend that nobody could explain. A planet this far from the sun shouldn't have much happening in its atmosphere at all. There was no obvious energy source driving this change, no clear mechanism causing this cooling. Scientists had pieces of a puzzle, but the puzzle made no sense. For 30 years, Uranus remained what one researcher described as a cold case, a planet literally rolling on its side with a magnetic field that seemed to be falling over, and an atmosphere quietly losing heat with no explanation. The question was real, the data was real, the mystery was real, but the tools to solve it simply did not exist yet. That changed when an international team of astronomers led by Paolo Trani of Northumbria University decided to point the most powerful space telescope ever built directly at this 30-year mystery. For 15 hours, nearly one complete rotation of the planet, the James Webb Space Telescope stared at Uranus without interruption. Using its near-infrared spectrograph, Webb did not simply take a photograph, it performed something far more precise. It collected over 1,000 individual slices of data from the planet's upper atmosphere, building, layer by layer, the first ever 3-dimensional map of what exists up to 5,000 kilometers above Uranus's cloud tops. As Trani described it, for the first time, scientists could see Uranus's upper atmosphere in 3 dimensions. Webb's sensitivity allowed them to trace how energy moves upward through the atmosphere and see the direct influence of the planet's magnetic field. This had never been possible before, not from the ground, not from any previous space telescope, not from Voyager 2. For the first time, the layers of Uranus's atmosphere could be peeled back one by one, and what was inside was not what anyone expected. The 3-dimensional map revealed something that immediately stood out. Uranus's upper atmosphere is not uniformly cold. As you move higher above the cloud tops, the temperature actually rises, peaking between 3,000 and 4,000 kilometers altitude, where the atmosphere reaches around 150 degrees Celsius. But here is what matters most. Webb's data provided the first definitive confirmation that the cooling trend, the one that began in the early 1990s and puzzled scientists for 30 years, is real. It is still happening. Uranus is without question still losing heat from its upper atmosphere. This is no longer a theory based on incomplete ground observations. This is a measured, confirmed fact from the most advanced observatory ever constructed. But solving one mystery immediately revealed another. The map also showed that the density of charged particles, ions, in the atmosphere was far weaker than scientific models had predicted. And critically, the ion density peaked at a completely different altitude than the temperature did. Temperature peaked between 3,000 and 4,000 kilometers up. Ion density peaked around 1,000 kilometers up. Two separate peaks, separated by thousands of kilometers. This told scientists something important. Whatever was heating the atmosphere and whatever was creating the charged particles were two entirely different processes happening in two entirely different places. Something complex was moving energy through the atmosphere of Uranus, and it was not what anyone had modeled. To understand what that something was, you need to understand just how strange Uranus actually is. Most planets in our solar system are relatively well behaved. Earth's spin axis and magnetic axis are roughly aligned. The North Pole and the North Magnetic Pole are neighbors. This gives us a stable, predictable magnetic field. Uranus ignores all of that completely. First, the planet itself is tilted nearly 98 degrees on its side. It does not spin upright like most planets. It rolls around the sun like a barrel. Then, its magnetic field is tilted an additional 60 degrees away from even that tilted spin axis. And then, the magnetic field is not even centered inside the planet. It's offset, displaced from the core. The result is a magnetic field that does not behave like any other in the solar system. As Uranus rotates, its magnetic field tumbles and wobbles chaotically through space, never stable, never predictable, constantly shifting. This bizarre magnetic geometry means that Uranus's auroras do not form clean rings around the poles the way Earth's or Jupiter's do. Instead, they are complex, dynamic, sweeping across the planet in patterns that scientists could previously only model, never observe directly. Webb changed that. The three-dimensional atmospheric map revealed the most detailed picture of Uranus's auroras ever created. Two bright auroral bands were found exactly where models had predicted, near the planet's magnetic poles. But between those two bright bands, Webb found something that had never been seen before: a distinct dark region, a gap where both the atmospheric glow and the density of ions were dramatically reduced. This dark gap is direct visual evidence of the strange magnetic field at work. It is a feature created by the shape of the magnetic field lines themselves, either funneling charged particles into the atmosphere or failing to do so, depending on the constantly shifting geometry of that tumbling, off-center magnetic field. And for the first time, Webb showed exactly how deeply these magnetic effects reach into the atmosphere. As Trani noted, by revealing Uranus's upper atmospheric structure in this level of detail, Webb is helping scientists understand the energy balance of ice giants. And that understanding is a crucial step towards characterizing giant planets beyond our solar system. The 30-year mystery is solved. The cooling trend is confirmed and explained. The magnetic field is the driver. The aurora structure is visible for the first time. The three-dimensional atmospheric map exists where before there was nothing. But what Webb has also done is show exactly how much we still do not know about this planet. Uranus is not the quiet, featureless blue ball that scientists described for decades. It is one of the most dynamic, complex, and scientifically valuable objects in our solar system. And Webb has only just begun to show us what is actually there.